Hello everyone, how you doing? I hope that we have all recovered after our first test. It's a big deal. It was a big test. I appreciate everyone's hard work and really coming at this thing studying hard. I'll be grading them soon and hopefully everything looks great. Today's lesson is going to be about derivatives to memorize. There are certain derivatives that we'll talk a little bit in class and stuff about where they come from and how they get there, but long story short, these are derivatives that need to be memorized, and they need to be memorized accurately. So let's take a look at, we're going to look at some derivatives of some trig functions, exponential functions, and logarithmic functions, so to complement our power rule that we already know. So let's start by doing the power rule, writing it again. I just want to show you a little bit different notation for doing a derivative. So when we see d dx here, d over dx, that means we're doing the derivative of the expression ax to the n with respect to the x variable. Most of the derivatives that we'll be doing this year are with respect to the x variable, although sometimes in contextual problems it'll be d dt, right, or things like that. But this is just saying what happens when I do the derivative of ax to the n. So again, just think about your power rule. What would the derivative of ax to the n be? Well, go ahead and write the answer. You should know it. If you don't, here's what it is. It is anx to the n minus 1. So again, this is like AKA the power rule. We know that when we want to do a derivative, we take the power, multiply it by the coefficient, and reduce that power by 1. Let's start with, or let's do one more of things that we know. What happens when we do the derivative of a constant? So for this one, c is a constant, so maybe c is 5 or negative 10 or pi or e. What do we get when we derive a constant? Well, anytime we just have a constant value, we take the derivative of it. Our derivative is always equal to 0. Just good to write it down. Let's get into some trig functions now. Let's go ahead and take a look at what is the derivative of sine x, right? What is going to be our derivative function of the function y equals sine of x? Well, the derivative of sine is cosine of x. In class tomorrow, I'm going to take a look at a sine graph and see if we can kind of make sense of that with the values. To see why it's obvious that this works. So the derivative of sine of x is cosine of x. Again, something that needs to be memorized. We'll be using it all the time. The next is the derivative of cosine of x. This one equals negative sine of x. The derivative of cosine of x is equal to negative sine of x. The last trig function that we're going to talk about today is tangent, the derivative of tangent. The derivative of tangent of x is secant squared x. Just a reminder on secant squared x, that means we take the function secant x Can we square the entire thing, the whole quantity, secant x? It does not mean secant of x squared. It's not the x that's being squared, it is secant of x, that the whole thing is being squared. That's the type of notation they use to show that it's the whole function squared, not just the x. Okay? So those are three that we need to have memorized that we're going to be using over and over and over again throughout this year. Also, let's talk about exponentials. We're going to look at the derivative of a to the x. A, again, is going to be a constant. A here must also be greater than 0. So A is some positive constant here. When we have the derivative of a to the x, we get itself back. We get a to the x multiplied by a number. And that number that we multiply by is the natural log of a. So the derivative of a to the x is simply a to the x times ln a. Okay. Now, so that would mean the derivative of 5 to the x is 5 to the x ln 5. The derivative of 10 to the x is 10 to the x ln 10. I want you to think about this. What would be the derivative of e to the x? Well, following our formula from the right above it, it should be e to the x times ln e. Well, the cool thing about ln e is we know that the natural log of e is simply 1. So it's e to the x times 1, which we can just write as e to the x. So our derivative of e to the x is e to the x. E to the x is its own derivative. All right, just to show you on your calculator here, just to make sure, we can see that ln of e is in fact 1. Again, when we think about what logs mean, natural log is log with a base of e. So e to what power gives us e? Well, e to the first power equals e. Okay. One more that we're going to look at today is the derivative of the natural log of x. And the derivative of the natural log of x is equal to 1 over x. The thing to think about, right, if we think about domains, right, e to the x, the domain is all real. Sine of x, the domain is all real. Cosine of x, the domain is all real. We do have domain problems with tan of x, however, right? We remember that tan of pi over 2 was undefined. Same with 3 pi over 2. Same with 5 pi over 2. Same with negative pi over 2. Right? So tan has some domain issues. Every once in a while, if we think about the graph of tangent of x, we have a vertical asymptote. Think about the domain of the natural log of x. Right? We can't do natural log of 0, and we can't do natural log of negative numbers. The domain for ln x is, the domain has to be all numbers x greater than 0. So just thinking about, like, I wouldn't do the derivative of natural log of x at an x value of -2 because that's not in the domain of natural log of x. Okay, so you guys, some of you guys were making some note cards before. I would strongly suggest making a note card with these things on them. Start studying them now so we can commit them to memory and we can solve these problems a lot easier. It's just like the times table. Life is so much easier when you have the times table memorized. Same here. These derivatives, it's really important to have memorized. What I want to do now is just a couple of sample problems. And we'll mix in finding derivatives at a numerical value, as well as writing equations of tangent lines. Okay. So let's think about the function. We've been using f and f prime a lot and g prime a lot. I want to use more dy dx, just to get you used to this notation more. So if we say y equals sine of x, the goal here is we want to find out what is dy dx evaluated at an x value of pi sixths. Okay? So let's think about this, right? This is another way of asking the same exact question. Is defining f of x equal to sine x, find f prime of pi over 6. What I want you to do is, whichever notation is used, the notation on the left or the notation on the right, they are exactly the same thing. They mean the exact same thing. In both cases, we're finding the slope of the tangent line at an x value of pi sixths. So whichever way is given, we need to know how to do this. Okay? So before we evaluate, right, our derivative at a point, we just need to find the general dy dx equation, or f prime equation. So first, let's find what dy dx equals. Well, what is the derivative of sine x? Well, we know from our derivatives to memorize on the previous slide, we know that the derivative of sine of x is cosine of x. Therefore, what would be dy dx evaluated at an x value of pi sixths? Well, that would be cosine of pi sixths. Uh-oh. Guess what time it is? It's unit circle time. What? We have to know our unit circle very, very well, not just for pre-calculus, which you all did last year or this summer. We have to know it for calculus too. Dang it. Okay, so what is the cosine of pi over 6? Well, let's think about our unit circle. Pi 6 radians, right? What is that point there on there? This is the one that's pi 6 right here. We know that is the point, root 3 over 2, comma half. All right. Might be a good time to start familiarizing yourself with the unit circle. Remember, the x is the cos and y is sine. So we know cosine of pi over 6 is root 3 over 2. Let's just use our calculator here to prove that this is true. I'm going to do this through the graph. So go ahead and get your calculator out too and do this with me here. I'm going to graph the function y equals sine x. When I graph y equals sine x, I get that sine curve that we know and love, that you guys all had to graph ad nauseum in pre-calculus. What I want to do now is calculate the derivative at the x value of pi sixths and see what we get for an answer. To do the derivative through your graph and calculator, again, we want to hit second and then the trace button. And we want to go down to derivative. Derivative is number 6, dy dx. So we'll touch number 6. And they want to know the x value that we want to do the derivative at. Well, the x value we're going to type in is pi over 6. So let's do that. We'll type in pi, there it is, over 6. And it says dy dx equals 0.86602526. By the way, if your sine graph doesn't look like mine, odds are your calculator is not in radians. Go ahead and change that. Remember, we changed that by hitting mode and going down and making sure radian is highlighted. Mine obviously already is. So we got that 0.866 number. We're supposed to get root 3 over 2. Let's just prove that root 3 over 2 has the same decimal. And we see that, yes, in fact, it does. So we know that our work we did was accurate. Let's do one more example, and then we'll call it a day. Okay, so here we have f of x equals the natural log of x. I want you to write the equation of the tangent line to f at x equals 1. Okay, so because I'm asking you to write an equation of a tangent line, we need two things. You should automatically be writing these two things. Point, slope. Well, we already know part of our point. We know the x part of the point is 1. What is the y part of the point? Well, to figure out the y part, we just want to plug 1 into our function, ln x here. So when I plug in 1 for x, I get the natural log of 1. So I could write ln 1, or I could be really smart and know what ln 1 is. ln 1 is simply 0. E to the 0 power equals 1. So I have the point 1, 0. Because f of 0, f of 1, my bad. F of 1 equals 0. Okay, now to find the slope of the tangent line, I need to plug in 1 to the derivative f prime of x. So first let's find f prime of x. We know from our table from before, the derivative of natural log of x is 1 over x. So if I wanted to find f prime of 1, that would be 1 over 1, which equals 1. So my slope is 1. They're all very nice numbers, easy to work with here. Okay, now I'm going to write the equation of my line. I'm going to say y minus 0 equals the slope times x minus 1. Now this is a perfectly fine answer here, right? But we could also write this as y equals x minus 1, right? We could simplify it down to y equals x minus 1. What I want to do now is prove that this really is the tangent line equation to the natural log of x at an x value of 1. So what I'm going to do is I'm going to graph my original function, natural log, and graph my line and see what it looks like. So go ahead and go to your graph. Oops. Go to your graph. I don't know why that was being weird. Okay, so I'm going to graph ln x. I'm also going to graph my equation of my tangent line, which simplified to x minus 1. Okay, and when I look at this, hopefully we see a nice tangent line. And boom, there you have it. See that beautiful tangent line right there? Also notice the graph of ln x. It's really easy to see that ln x has a domain x greater than 0 there, right? We don't see any negative or 0 values for natural log of x. So, have fun with this. Memorize those derivatives. They're going to be important all year long and on test day. So, that's all I got for you today. Have a good one. Peace.